Section 15.2 in the Stewart's and 15.2 and 3 in Thomas's textbook. What if the region, the closed region which you performing the double integral is not rectangular region anymore? What if it's a general region like so? So now what? Well, in that case, we go back to first semester calculus and see how did we go about finding the area between two curves. Well, if you had functions, then you took a rectangular element between the two functions. So the width of that rectangular element was dx, and the width was y of the top minus y of the bottom. So the area of this region trapped between these two curves is f of x minus g of x as x goes from a to b dx. Remember, this is what? Top curve. And this is what? The bottom curve. So that's top minus the bottom times dx. Because this gives you the what? Let's say the length. This would give you the width. And you multiply the length by width, you get the area. And then you got a bunch of these kind of boxes or rectangles. You add them up, and lo and behold, you get the final answer. However, type 2 is, what if you are trapped between two relations as opposed to functions? In other words, up here I took a what? Vertical element. What if I take my element to be horizontal like this? Horizontal element. How would that put a dent in my area, computation of the area problem element? Do you see it? In that case, the width of the rectangle is dy, but the length is x right minus x left. So this is x right minus x left. So in this case, x left is a function of y, and x right is different function of y. Remember here they were function of x's. In this scenario, they will be functions of what? Y's. So this would be like what? This would be like, say, the right curve minus the what? Left curve times dy. So these limits are for y, whereas before the limits of your integration for x's. However, in multivariable calculus, we have, let's say we're trying to find the area between two curves. Remember, we decided what? If the function is equal to 1, this double integral finds the area between these two curves. Instead of going what? Top curve minus the bottom curve, when you take the element what? Vertically, like so. In this case, we go what? Y of the bottom. That would be the limit of the first integral all the way to the y of the top. Notice the first integral now it has variable what? Limits. However, the second integral, the outer integral, is always constant, rain or shine. So x goes from still a to b. But those limits, remember in first semester calculus, we had f of x minus g of x. Now they appear as the limits of first inner integral. And we go y bottom all the way to y top is the lower limit and the upper limit. But notice the order, that's dy dx, not dx dy. Because in this scenario, in this section, the order matters now. Do you see it? However, if you go dx dy, so now you're taking your element what? Horizontally. So now you have to go left curve all the way to the right curve. In other words, the limits of the first integral, the inner integral, will go from left to the right. But then again, the outer integral will be constant. So this would be the what? Limits of y, which goes from c to d. So notice the difference. What was happening in Cal 1? What's going on in Cal 3? They, all of these four, what? Like the, like this guy, number 1 and number 2, they find the same area. And number 3 and number 4 also finds the same area for this. So do you see it? 3 and 4 finds the area for type 2. 1 and 2 find the area for type 1. Except instead of single integral, now we're using double. Rain or shine, the outer integral will always have what? Constant limits. You will never, ever have a variable here. Never, right? So double integrals over general regions, what? The order matters. It matters how you integrate. Are you integrating with respect to y, then x? So that means you're taking the element vertically. Are you taking the integral with respect to x and then dy? Then you taking the integral, what? The rectangular element horizontally. So this guy goes for dx dy kind of a problem. This guy goes for dy dx kind of a problem. So keep that in mind because it's super important. The order is important. Suppose we like to what? Evaluate this integral, all right? So what is the limits and how do you graph the region? Remember, when we say graph the region, that means graph the limits of the integration, not the integrand, because sometimes students graph this. When we say graph the region of integration, R stands for region of the integration. Is that right? Graph the what? The limits of the integration. Okay, watch this. X goes from 0 to what? Y squared. And y goes from 0 to 2. So graph this. This is your region, which came strictly from the what? Limits of integration. Okay, x equals y squared is this parabola. Y is equal to 2 is this horizontal line. So this is x equals y squared. And y goes from 0 to 2. So looks to me they are talking about this region. So that's the region, the closed region of integration for this what? Double integral. Okay? So now the question is, how would you go about what? Setting the limits. Even though I have the limits, let me just show you how would you set up the limits. Let's say this is your integrand and you want to go dy dx and all you have is just a graph. So how would you set up the limits? Dy dx means you take your element, the rectangular element, what? Vertically. So looks to me, the bottom of this element is lying on this what? This curve. So that would be what? Y equals what? Square root of x all the way to y equals 2. So from here to here, notice the bottom is what? The bottom of this rectangular element is on this curve, whose equation happens to be what? Y equals the square root of x. And the top is y equals 2 because it's a what? Horizontal line. So it's constantly equal to 2. But then x goes from 0 to what? Whatever this guy is, which happens to be, I believe, 4, 2. So this would be like 4. Is that right? So that's one way to set up the integral. Do you all see it? On the other hand, if I had, let's say, taken my element horizontally, so let's say this is the graph again, like so, and here is my region. So now this time, remember this is my region, I'm going to take the element this way. Is that right? So now I have to go, what? X squared, what was it? Y, I believe this is Y. Is that right? What? Dx dy. So I'm going dx dy. Obviously the order matters. So looks to me the left side of this rectangle is sitting on what? On what? Y-axis. But the right side is what? Sitting on what? The parabola. And y goes all the way from what? 0 to what? 2. So did you notice there are two ways to set up this what? Double integral of x squared y. If I go dy dx, these would be the limits. If I go what? Dx dy, this is how the limits go. So the moral of the story is what? The order now very much matters, because for each kind of setup, whether you take your element vertically or horizontally, the limits drastically change. However, in both scenarios, the outer limits will be always, rain or shine, constant. You'll never ever have x or y for limits of outer integration. Do you see it? So how would you evaluate this, you ask? Well, what you do, just like before, you evaluate the what? Inner integral first with respect to x, so you keep the y's constant. So this guy goes for the right, but the integral of this guy is x cubed over 3. But x goes from 0 to y squared. First, you replace this x with y squared, then replace it with y, so that gives you y to the 7. Right? Because that would be y squared to the third is y to the 6 times y is y to the 7. Is that right? And there goes the 1/3. And now you are back to single variable integrals. So integrate that with respect to y, and you get 1/3 y to the 8 over 8, 0 to 2, and then there is the answer. Always graph R on xy plane to determine the limits of integration. R meaning what? The region of integration, not the what? The double, or I should say, function of two variables, not the surface, but the region of integration. Either they will what? Give you as a limits of integration, or they will give you some kind of information about how the region should look like, or the equations of the region. For instance, notice they want to evaluate this double integral over this region, all values of xy, where x goes from 0 to 2, y goes from 0 to x. Y equals x is this 45 degrees line which goes through the origin. And x is equal to 0 to 2 is this guy, right? And x is equal to 2 is just vertical line, so the region is this triangular shape. So if you go dy dx, so the bottom of the rectangle here is on the x-axis, so that would be like what? Y equals 0. The top is on the what? Line, it's not constant, and y is equal to x. And x goes from 0 to 2. Do you see it? If you do the integration with respect to y, keep the x's constant. So now, basically what you got is what? This answer, okay? Because remember, you can let u be x squared minus y squared, but keep the x's constant. du, which is negative 2y, is almost out there. So you need to compensate for that. Do you see it? So now the idea is now what? If you integrate this with respect to y, you get this. And then you evaluate it between what? Y between 0 and x. You get a function of single variable. And now you're back to first semester calculus, and lo and behold, you have it. On the other hand, sometimes one way of doing the limits either will, take you to impossible integrals. You won't be able to integrate it, or the integral will be so complicated, which is not even worth it to try. For instance, if I would have done the same problem taking the what? Horizontal limit, then here I have to go from left curve to the right curve, and then I have to keep the y's constant first, but then I don't know what the derivative of x squared is, which is 2x, and there is no evidence of it anywhere in the integrand. However, you can manipulate this and then perhaps use trig substitution and let secant of theta to be x over y. You could, but that's a very long process. The moral of the story is I should know both ways to what? To set up the limits of integration, see which one takes you to the answer faster. So it's not matter of preference. Sometimes it's matter of necessity. I have to set up the integral one way over the other way. This problem is evaluate this integrand xy. Notice they didn't even tell you the order of integration, so they left it up to you guys. Should I go dx dy or should I go dy dx? And the region is this semicircle in the what? 1/4 of a circle in what? In the first quadrant. X is positive, y is positive. So if you go dy dx, so that means you take in vertical element. So y goes from 0, the x-axis, all the way to the what? To 1/4 of a circle. But if you evaluate the inner integral with respect to y, keep the x's constant, so x goes for the right. And then when you replace the y squared with the square root of 1 minus x squared and 0, this becomes extremely easy integral. Now we are back to what? First semester calculus. Notice the bottom limit is what? Bottom curve, which is the x-axis. The top limit is the top curve, which is the quarter of a circle. Do you see it? But notice the outer limit still stays constant. Do you see it? So with that in mind, I can now do a volume problem, and that should pretty much do it. So question is, find the volume of the solid bounded by this elliptic paraboloid, which has been shifted 1 unit above the what? Origin, and the planes x equals 0, y equals 0, z is equal to 0. Check this out. When they say z is equal to 0, that means the bottom of the what? Solid is on the floor. And x plus y is equal to 2. Is that right? So that's kind of like 2, right? Which is y is equal to 2 minus x. So you graph not any of these, just the region. The region is what? X equals 0, which is the y-axis. Y equals 0, which is the x-axis. And this line, whose slope is -1, and the y-intercept is 2. Here is your region. Do you see it? So now to find the volume, you got to use this formula. Double integral z top minus z bottom, which is the height of your typical box, times the area element dA. You decide whether you should go dy dx or dx dy. It's entirely up to you. I went dy dx because I took my element, but vertically. So what does that mean? That means z top is the elliptic paraboloid. Z bottom is the floor, which is 0. And now I'm going from what? Bottom curve, is that right? Bottom curve to what? To top curve. Notice these are not necessarily what? Constant, because you are no longer on a rectangular region. Only rectangular region give you all these four limits as constant numbers. Do you see it? And what do you know? When you evaluate this straightforward evaluation, you get what? 14/3 cubic units. So that's really, really super nice. So let's finish this section with one general example. Make sure we know how to do this. Suppose you were given 0 to 1, tan inverse of x to pi over 4, fxy dy dx. Question is, reverse what? The order of integration. The order of the integration. Is that right? Sometimes they say change the order of integration. So reverse, change, all same thing, right? So what do you do first? First, you graph the region. Graph the region of integration, the region of the integration. And remember that region supposedly should be a closed region. It should not have any holes in it, no opening. So by the looks of it, notice y goes from what? Tan inverse of x to what? Pi over 4. And then dx, which stands for limits of x, x goes from 0 to 1. Is that right? So how does this guy look like? Well, tan inverse of x kind of looks like this. So if this is pi over 2, this is like what? Negative pi over 2. Here is how tan inverse looks like. Do you see it? And guess what? Y, and it goes up to what? Pi over what? 4. So that would be halfway here. So it looks to me we're talking about this region right there. Is that right? And because I had dy dx, they must have took the element what? Vertically. Now, I think they want you what? Evaluate. Notice I don't know how to evaluate this because I don't know what this guy is. All I can do for you is what? Reverse the order of limits or integration. I don't know what that guy is. There's no way I can come up with an answer. So now they want you what? Instead of going dy dx, go dx dy. In other words, if this is my region, they want you what? Take a horizontal element. Okay. So in other words, tell us what the values of x is first, and then tell us what the values of y should be. Do you see it? First x's, then y's, which is opposite of what we had to begin with. Here we had the limits of y's and then x's. Up here, I want to know what the limits of x's is, then y's. In other words, I like to reverse, or as they say, change the order of integration. Okay, looks to me, x goes from 0, which is the what? Y-axis, to this guy. Okay, but what is that guy equal to? Well, that guy was equal to y is equal to tan inverse of x, which is identical to saying x is equal to tan of y. If you just take the tangent of both sides, you get x equals tan of y. So x goes to tan of y, and y goes from 0 to what? To pi over 4. Is that right? So There you have it. Now, if you would do this integral, provided you know what this guy is, which I don't, because all I was asked to reverse the order of integration. Hopefully, God willing, if nothing goes wrong, these two what integrations should give you what the same answer. But check it out. The limits, no way they what come close. This guy goes from 0 to what? What was it? 1. Is that right? 1 for x. Whereas here, y goes from what? 0 to pi. Up here, y goes from tan inverse of x to pi over 4. Here, x goes from 0 to tan of y. So it's not matter of just switching the limits. It's matter of graphing it and then drawing your rectangular box, and off of your graph, come up with the correct what? Limits, right? Good luck. Thank you.